Hey guys, today we're going to learn physics. So to start off with, I have a Desmos thing open with 4 different folders. They're all empty right now, but I would recommend starting off with them so you don't lose track of what's going on. To start off with, there's a slight problem. Whenever you reload the tab, let me just do it quickly. As you can see, the objects have different radiuses. You see how it ends in 0.46 and not like 0.40, which would be nice. This one's fine. It ends in the 0.0. But what we're going to do to fix this, first off, is we're going to make it so as small as possible. Because now, if you make it bigger again, it'll end in 0.0, which is good. We want that to happen. So let's do the same thing for 0.2. And oh, look at that. It's fixed. We have normalized the mass. Pretty cool. And I'm just going to keep my objects at 470 grams for kilograms for now. And then we'll go from there. So, to start off with, we are going to make a new, we need to make the folder open first. We're going to make a new line, so this little line connects them. We're going to add a table. We're going to call our first set of values, we're just going to do mass, M1. Then it will be our force that is due to the mass. The force of gravity due to the mass. So FGM. Right? And you know what? I'm going to use a different mass than what I've done previously. So I'm going to make it, say it's a bit bigger. 3.76. And I'll keep them the same because I'm really lazy. So just keep that in mind. Our mass is 3.76 times 10 cubed. So I'm just going to write that down actually. M1 and M2 are both 3.76 times 10 cubed kilograms. Yeah, you can just write it down right in Desmos. It's pretty neat. Alright, so let's get started. So we're gonna keep changing object 1 because we called it M1. So to start off with, we'll just start here and then, first we need to set a constant distance, right? I'm gonna make it really far away. So I have room to get as big as I possibly, actually we'll keep it like, I don't know. We'll just keep that one like there. And we'll keep this one really far to the right, and then we'll keep this one a bit closer. So it has room to get like really big, right? So we'll keep our constant distance at constant, not tan. Let's call it constant distance. Oh wait, it doesn't like that either. How can I phrase that? Just say this equals 12 meters, right? And remember, we're going to keep that constant, and we're going to keep track of it. That's why I wrote it down in Desmos. So, to start off with, we can just use whatever our first value is right now. Our 3.76 times 10 cubed. That's our first mass. Now, if we use our force, it'll give us a number. But I don't really like that number, because it's not very precise, and precision is the spice of life. So what I'm going to do is just figure it out myself, because I don't like the way it doesn't give that much precision. So this is your formula for finding the force due to gravity, right? We're just going to leave that here for a second. And so we're changing M1. M2 is still, remember, it's still 3.65 times 10 cubed. So we'll leave that there. If I can type, that is. Times 3.65 times 10 cubed. And then we're going to change M1, and in this case, we're starting off with the, 3.76. Did I actually keep it like that? Oh, wait, no, they're both starting off with 3.76. My bad, guys. Apparently, I just don't understand how the vision works. So, I'm going to start that off at 3.76, everything. 3.76 times 10 cubed, and then we'll make the mass 2, 3.76 times 10 cubed. Oh, sorry. This is M2, this is M1, because M1 and M2. So we'll just get rid of M1. And now our R value remember, we wrote it down. It's 12 meters, so we're just going to plug in 12. And our G value is 6.67 times 10 to the negative 11, because it says it right here. Look at that, 6.67 times 10 to the negative 11. That gives us a force value. Yes, 6.7. That will give us our force value that we're going to put in over there. And if you really, really want this in micronewtons, just to check if your answer is actually like similar to what the calculator gives you, just do this. And then just take away 6 here. So 1, 2, 3, 4, 5, 6, 6.5. So it should be about 6.5 micronewtons. Look at that, 6.5 micronewtons. Except with more precision, because that's cool. So there we go. That is our first value. Now we have to do this 10 times. Okay, so let's make mass 1 a bit bigger. 5 times 10 cubed now. 5 times 10 cubed, right? Sorry, 5.00 times 10 cubed. Now, our mass 1, we're changing now to 5.00 times 10 cubed. Mass 2 is still the same. G is still the same. The distance is still the same. This is our new force. And this is the same thing as how many micronewtons? 1, 2, 3, 4, 5, 6. 8.7 micronewtons. Look at that. This and this are the same. So this is our new micronewton value. Just to double check. Yep, 8.7 micronewtons. Pretty cool. Now we're going to do it again. We're going to make mass 1 another bigger. 6.49 times 10 cubed. And we're going to substitute that in for M1. Then we're going to take this value. We're going to stick it over here. Multiply by 10 to the negative 6. 1, 2, 3, 4, 5, 6. Should be about 11.3 micronewtons. We'll just double check that. That is what the calculator says. Oh, sorry, wrong place. Should be a... What? There we go. Now for number 4, gonna make it a bit bigger. 8.25 times 10 cubed. And yeah, if you haven't figured it out, this takes a while. It's actually quite the pain. Negative 6. 1, 2, 3, 4, 5, 6. Should be around 14 micronewtons. 14 micronewtons. Yeah, 14.4, which is like 14.36 when it rounds up. Now next we're going to make it even bigger. 1.03 times 10 to the 4th. We're going to stick that in there. We're going to repeat the same process. 1, 2, 3, 4, 5, 6. Should be about 17.9 micronewtons. It is. Good. Now for our next value, 1.27 times 10 to the 4th. 1, 2, 3, 4, 5, 6. Should be about 22.1 micronewtons. It is. Good. Gonna make it a bit bigger. 1.54 times 10 to the 4th. Substitute that for M1. We have our new force. And when you guys set it equal, so 1, 2, 3, 4, 5, 6. Put the point. Should be around 26.8 micronewtons. It is. That's good. Let's do that. How many are we at? 1, 2, 3, 4, 5, 6, 7. 6, 7. Now we're going to do it 3 more times. We're almost done with the first part. 1.85 times 10 to the 4th. Stick it in here. Do that. Do this. One, 2, 3, 4, 5, 6. Point should be around 32 micronewtons. I'm not going to check anymore because I know I'm right. So, wait, hold on. I don't think I was right for a second. 32.1. 32.2. Uh-oh. What did I do wrong? You know, sometimes I say I know when I don't really know. This is one of those times. But look, 32.1, 32.2, it's close enough, right? We're just going to say it's fine and move on. Object 1 is 2.19 times 10 to the fourth. We substitute that again. That's our value. What the heck happened? Negative 6. 1, 2, 3, 4, 5, 6. Should be around 38 newtons or so. 38.1. 38.1. Okay, this one's fine. So, how many are we at? 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. Then you can stop doing this part. 2.58 times 10 to the fourth. Substitute 1 the last time. 1, 2, 3, 4, 5, 6. Should be around 44.9 newtons. It is 44.9 newtons. Look at that. Data. Now let's try and see our data, because seeing is important. So it's about 3.7 times 10 to the third to about, I don't know, 2.6 times 10 to the fourth. Now it'll be about 6.5 times 10 to the negative 6 to about 45 times 10 to the negative 6. And we'll zoom out, and boom, that is our data. And as you can see, it's pretty linear, which makes sense. Because if you look at our formula, do I have it here? I don't, but it's in our formula sheet. The formula for gravity, mass should be proportional to force. So that means we did it right. Whenever you change your mass and keep everything else the same, it should make a line with, yeah, it's a line. All right, now we're going to leave these values here for now. We'll come back to them in a minute. And we have finished that part of the problem. Pretty nice. So we'll close this, move on to newtons times distance. We're going to do pretty much the same thing. It's just that we're going to hold different things constant. So let's go back to this position right here. Our distance should still be 12 meters. If you take a look at the ruler, it's still 12 meters. Now we need to set them both to 3.76 times 10 cubed. 3.76. There we go. 3.76 times 10 cubed. Now we are going to vary the distance instead. So we're going to change it to D1. Now we're going to change the other one to F, the force of gravity, due to distance. Oh, and we're going to hide the other folder. Because we're going to make it hide. We're going to make it sit still for a minute. Alright, and for our calculation purposes, we're going to bring back formula. So f of g equals g m1 m2 over d squared. And we shall let the math commence. So just to make sure, actually we're gonna bring our constants back. So m1 and m2 are still both that to start off with, and the distance is 12 to start off with. Or you know what? Let's change that. Start with. And then these ones, yeah, they stay like that. And distance starts with 12 meters. Alright, so we'll start off at 12 meters. And we'll take a look at our current force. It should be around 6.5 newtons. Or micronewtons, sorry. Let's just double check that though. So it should just be 6.67 times 10 to the negative 11 times the mass of our first object, which is 3.76 times 10 cubed, times the mass of our second object, which is, once again, 3.76 times 10 cubed. Then we'll divide that by the distance squared, just 12 squared, and you get this number. Divide that by 10 to the negative 6. 1, 2, 3, 4, 5, 6. 6.5 micronewtons, 6.5 micronewtons. Boom, first value done. Now, do you think we should make this bigger or smaller? Smaller. You better make it smaller. So, instead I would go every meter, but I'm pretty sure that'll cause you to run out of space. So we're just gonna go every 0.2 meters because it does the exact same thing. You will get the same shenanigans to occur. So, we're gonna have our new distance as 11.8. Now, we're going to find our new force. We're going to change this to 11.8. Have our new force value. Do this. Do that. 1, 2, 3, 4, 5, 6. 6.7. And we'll check if it's around 6.77 newtons. 6.8 newtons. Yeah, checks out. Alright, we're going to do it for 11.6 now. It's 11.6 newtons. Should be around 7 newtons or so. Look at that, 7 newtons. Next up, 11.4. Alright, 11.4. Should be around 7.25, so 7.26 newtons. Yeah, 7.2 newtons. Checks out. And we're gonna do 11.2 meters now. 11.2. Oh, wrong thing. 11.2. We're gonna substitute that for distance. That's our value. 1, 2, 3, 4, 5, 6. Should be around 7.5 newtons. That is correct. 7.5 micronewtons. We're going to change it to 11.0, and we're going to substitute that in. Should be around 7.8 newtons. It is. We're going to change it to 10.8. Oh, sorry. You got to do it here too. 10.8. And we're going to get our number, copy and paste our number, change it to micronewtons. Should be around 8.0 newtons, or 8.1, 8.1. How many are we at? 1, 2, 3, 4, 5, 6, 7. Okay, we have 3 more. So 10.6, 10.4, 10.2. And now we'll do them all. 10.6. Give you that. Change that to 10 to the negative 6. Should be around 8.3 newtons. Oh, sorry, do I have to change it? Boom. 10.6. 8.4 newtons. Oh, yeah, 4 newtons. I knew that. I can read. We'll change it to 10.4 now. And then we're going to change this to 10.4. We're going to take our new force. Whoa. Is that right? Oh, yeah, that's right. We had to move it first. I knew that. 1, 2, 3, 4, 5, 6.7. Should be around 8.7 newtons. It is. I'm going to do it for 10.2. Should be around 9.06 newtons. Yeah, 9.1 newtons. Alright, we have finished this one. Let's see how our data looks. And this is for changing the distance, keeping the masses constant. We're going to start off at about 10.2, or just 10, and then we'll go to 12. Or no, we'll make it 13, just to get that last part on there. Well, y-axis, we go from the top to the smallest part, so 6.5 times 10 to the negative 6, and then we'll go 9 times 10 to the negative 6. I'm going to zoom out, and there we go. Why is it a straight line? I actually don't think it's a straight line. So it shouldn't be a straight line. So we're just going to make a line. See, look how it's kind of off. That's how it should be. It shouldn't be quite accurate. What you're supposed to be able to do with this data is it should be proportional to the square of it. So if I were to do FGD equals A over D1 squared, and oh, sorry, not equals, that should be it would be pretty close to a quadratic. If we zoom out a lot, you can see that's not a quadratic, it's a inverse square function. Whatever, that's what I meant. And you see how it looks a lot better than a line, even though a line is pretty close. like, it's actually, this is a measure of how close it is. It's actually exactly the same closest. You can kind of visually see that a quadratic is kind of, or not a quadratic. The inverse square is a lot better of a fit visually. I don't really know why the line works so well. That's probably just due to the fact the numbers are so small and shenanigans are afoot. Anyway, this should be proportional to 1 over this squared, and that's that. Now we have our changing distance and we have our changing force. And that's pretty good. Now let's set our stuff back to this because it's just... What do we start off at? 12. We started off at 12 meters. And do we have our starting mass the same? 3.76? Yes, we do. Okay. And we're just going to do that. Now we have, to recap, we have our changed mass to get force, and we've changed our distance to get force. Now we're going to combine those to get our final answers. So, derive gravity. That's what I meant. So we're going to take our gravity formula that we've used about 7,000 times now. Now, in order to find G, we're going to have to set this into y equals mx plus b form. We're going to get rid of those three. I don't know how they come there. Right? Our b is irrelevant. As you can see, we are not adding anything. So b equals 0. We're just going to get rid of b. Now, fg is equivalent to y. And m is equivalent to g. That is our slope. We want our slope to be a constant number, because that makes a line. If we make our slope whatever the freak this is, it will not be a constant, and we will no longer be having fun. I mean, we're not having fun right now. We're doing physics, but anyway, m1 times m2 over d squared becomes our input, right? And in order for this to work, we need to set either the numerator constant or the denominator constant, because you can only change one thing at a time. If we used both the changing mass and the changing distance, all of a sudden nothing works anymore and you've successfully lost the plot. We are in this case going to keep our mass constant and we're going to use our changing distance. Because if you remember from before, whenever we did change our distance, we kept the mass the same, right? So let's do that. We're going to keep our input, which is this. We're just going to copy and paste that, bring it over here. And our M1, M2 were both 3.76 times 10 cubed, if I remember correctly, which I do. 3.76 times 10. I'm just kidding. I actually don't remember. Let me check. Yeah, 3.76 times 10 cubed squared. And we're going to do that divided by the distance squared. Actually, oh, D1. That's what I had it as. That's why. Boom. It does math for us. Isn't that great? Hate doing math. And then we're going to set our y values equal to the force that was gained from changing the distance. So that would be this stuff over here, f of GD. F GD. And as you can see, nothing shows up because you have to put a 1 in front, because I don't know why. Now, let's take a look and find our data. So we know what to do. 98,000 or so to about 136,000 or so. Then 6 times 10 to the negative 6 to 9.1 times 10 to the negative 6. Zoom out, and boom. Our data is a perfectly straight line. Isn't that good? That's very good, actually. We're going to hit this magical button over here. And look at that. We did it. Our slope of our line is, in fact, G. We figured out the gravitational constant with a 100% accurate thing. Oh, I'm tired. But we're not done yet, because we can do it a different way, too. We can do the opposite. We can take the distance constant and the changing mass. So let's do it, because we can. And we have free will. Right, we need to make the whole thing again. We're going to start off with our formula. We're going to get rid of these three. Do y equals mx plus b. Just to remember that. Get rid of b. Oops. Oh, no. This, that, and okay. Now we're going to build another table. And this time, we're going to keep the distance the same, because I put constant distance up here, right? So m1, m2, d squared is still our input, but now distance stays the same. Because remember, when we found changing mass, we set our distance to be a constant if when we change the mass of mass 1. So mass 1 is still going to be mass 1. That's what I have it saved as, mass 1. And we're going to multiply it by whatever our mass 2 was, which is the same every time, just 3.76 times 10 cubed. And that's that. That'll give you m1. And then in the denominator, our distance was constant. Our constant was 12 meters. So we're just going to do 12 squared. Gives us some values. If you notice, the first value is coincidentally, if I can use my mouse, that is, it's exactly the same, which makes sense. We're starting off from the same position. That means we're doing something right, which is good. If you're not doing it right, then you're doing it wrong, which is bad. So anyway, our output should be our forces. And we set those forces for when we kept the changing mass. We kept that as FGM. So let's keep it FGM. And it shouldn't work until we put the 1 in front. And boom, magic. Now, let's check if we do our math right. Or, sorry, we need to see our values. 98,000 to 700,000. Our y-axis goes from 6.5 times 10 to the negative 6 to 4.5 times 10 to the negative 6. Oh, sorry, other way around. Oh, it was the right way around. 6.5 times 10 to the negative 6 to 4.5 times 10 to the negative 5. Do that, zoom out, boom, we have a line. Now, we gotta find the slope of the line. We hit the magical button in the corner, and look at that. Gravity again, because you can do it 2 ways. And if we just go back to make sure that we, in fact, actually, if you look at that, that's actually pretty crazy. All of them are on the same line. The ones from the first one and the second one. Isn't that crazy? Oh yeah, these were the ones from earlier. These are the ones up here. Actually, let me make them a different color. Let's make it green. You can see them down here. There's the green ones over there. And then the blue ones are still on the exact same line because they have the same slope. And this part, the B, is so small, it's negligible. We can ignore it. We just solved for gravity by taking the slope of the line, and we are done. Yeah, so in summary, we found our mass, or, oh my god, that's force. Found our force with changing mass. We found our force by changing distance. Then we set one of them constant, we set mass constant, we compared the force to the changing distance, got the slope, did that. Then we kept the distance constant, we changed the mass, and we found the slope of that. It's the exact same thing. 6.67 times 10 to the negative 11. And that is how physics works. Thank you everyone for watching this video. Don't forget to like and subscribe. I hope this turned out well because I don't want to record this again.